to kick things off, I'd like to invite Franz, who's one of the architects of Google Translate. So over to Franz.
Thank you, Amar. Okay, so I want to talk about Google Translate. Just a quick question for the audience. Who used Google Translate before? Many hands go up. Anyone that didn't use it? Still a few hands go up? Okay. Nobody in your family used it? Okay. But it seems certainly the majority of people has used it before, and I guess the ones that haven't probably will after the talk. What Google Translate does is it's a service that you can use on the web, translator.google.com and various other places. And you can put in some text in some language and translate in 63 different languages. So here you see from Czech to English. And what you can also do, it's integrated in search. So if you're looking for some information and the best answer for that information would be written in a different language, then you can just go to search, type in your query in your favorite language, in English. And then when you do translated search, it suggests which language this might be an interesting, you might get an interesting answer. And then you basically get search results in that language where everything gets translated to English. So the title would be translated into English and the snippet would be translated into English. And when you click through to that search result, the web page of that restaurant, for example, would be translated into English. Another use, and we have it actually in many different products at Google integrated. Another use that we have is, for example, for YouTube. So Obama puts up his weekly address to the nation on YouTube, and it comes with caption information that's in English. And then someone can just say, I don't know English, I want to translate that into Arabic. And then basically the captions for that will be translated into Arabic, and you can, right, if you're an Arabic speaker, you can see what is said there. And we have it integrated in Chrome and various other products. So the idea is that whenever you would run into the language barrier, that you don't understand some text, or that you want to answer a question, and the answer for that question would be on a different language website. Whenever you run into the language barrier, the goal here is, right, technology will help you and you can understand what's there. So the approach we are doing is different from what you probably might think of how this could be done. So machine translation is a very old field. People originally have used a lot of rule-based approaches where you have linguistic experts that write down how to analyze a language and how to transform it into a different language and how to formulate then the words there in the sentences. And the way we are doing that is just the Google approach of using very large amounts of data, massive amounts of data from web, from books, and other material. And then basically with fancy magic machine learning, we learn from that how to mimic what humans do when they do translation. And so as a result, for most of those systems that we've built, so 63 different languages now, nobody in the team actually is speaking most of those languages. But it's still possible then with machine learning to basically build systems that way. So this shows over time how many languages we had. So we basically added most recently very small languages, at least small with respect to representation on the web, very large still with number of speakers. We added bunch of Indian languages, Bengali, Hindi, Tamil, Gujarati, and those languages. So now we have actually over 99% of the languages covered that you find on the web with respect to the material in which they are printed in. So one important point for the way we are doing machine translation is basically data. The more data we feed the system, the better the translation quality gets. So here you have a plot where you see basically for a bunch of different languages, for 1 million words on the left to 10 million words on the right, how translation quality improves. On the vertical axis, you see a metric which reflects translation quality. And in that metric, roughly, basically, if you have 0.2 in that metric, that means you have a reasonable translation quality that we are basically willing to expose a system like that to our users. And obviously, you want to have the metric is bound by 1.0, so you want to have as large a number as possible. So with 1 million words, right, very few languages are good enough. 1 million words is not too much. A book probably has something like 200,000 words. But with 10 million words, right, many languages already cross that line. And then if you go to 100 million words, translation quality becomes even better. And then if you go to 1 billion words, basically all languages are well above this 0.2 line. And again, so basically, data is a key in order to make this approach work and work well. So as data, we use typically data that comes from the web or from books to learn the translation. But there's basically other kinds of data which is the users themselves, in some sense, can collaborate in order to make the system better. And that's actually active research to use that kind of data. But the idea is that by users using the system and interacting with the system, in this case, basically users can see a translation. And if he doesn't like the translation, he can click on the words and get a list of alternatives and then say, oh, this one is actually the correct one. And then by that, edit the translation, but also provide a signal point that helps then to improve the system quality. So if later on a different user would see, it's less likely to get a similar mistake. And so some of the developments for the future, so something that we are working on currently, and is, I think, very, very exciting, is basically then to combine this with speech recognition and text-to-speech. And speech-to-speech translation. If you own an Android phone, you can download the Google Translate Android app, where then you have Google Translate integrated in there in this app. And you can actually then speak into that app. And for English to Spanish, you can also have a conversation then with a Spanish speaker back and forth communicating. And basically one person would speak into that and the other person can respond, and always basically gets mediated with speech recognition and translation. And so this is one of the, we have this out as an alpha version. So obviously a lot more work needs to be done to make their quality really good. And what it requires is really good speech recognition quality, really good translation quality, really good text-to-speech. And that's a good way to hand over to Vincent. He will talk about speech recognition.
Okay, thanks, Franz. So my name is Vincent Vanhoucke. I'm a member of the speech technology team here at Google. And I thought I'd try to share with you a single piece of insight that we gained from working on speech technology at Google scale. A lot of the machine learning that we do really uses humans as the benchmark, the golden standard. Both in machine translation or in speech recognition, human performance is what we're striving for. And as a consequence, if you ever considered to, how would we do superhuman speech recognition or superhuman machine translation, we could simply not get there because humans are the standard. So the first step might be to first get rid of other humans. You might wonder why I'm talking about superhuman speech recognition right now. We all know speech recognition right now is not at the level of human performance. The problem for us researchers is that it's getting dangerously close. I'll share with you an experiment. So I work mostly on Google Voice Search. It's an application that you can have on your phone. It's integrated in Android. It's also available on iPhones. You can just speak a search query, and the result pops out. People love it. It's a great user experience. It's a great UX, and we want to make it completely magical and transparent so that everybody can just speak into their phone. So imagine that you're talking to Voice Search. We're issuing you a query. We record that query, and then we play it back. We play it back either to yourself or to the speech recognition engine that's in your phone or that's in the network. There's no question that you will do a much better job at returning the right search result than the speech recognition system might do. Listening to yourself speaking, you will have no problem. Speech recognition is not yet at your level. Now, if we change the experiment a little bit and we replace you with another person, another human being, somebody who might not know you, who might not have the same cultural context the same, not live in the same place, or not really have the same background, then that becomes a toss-up. The naive human will not have any significant edge over the speech recognition system. Why is that? Roughly, really quickly, speech recognition has two parts. There is an acoustic model and a language model. The acoustic model is what translates sounds into phonemes. And that is not nearly as good as humans right now. The other piece is the language model. And the language model is what really predicts words and their pronunciations and how people might say them. That model we train on really large amounts of data. So for the voice search system at Google, we train it on 240 billion words. And those come from billions of users. It's a huge amount of knowledge that's embedded into the system. So any human being that might be listening to that audio might not have this vast amount of knowledge at their fingertip. If a person is not from Canada, they might not know how to spell Saskatchewan. If a person is not from New York, they might not know how to pronounce Schenectady, New York. And I'm probably pronouncing it wrong myself. So this is where the system has an edge. And it's a huge problem for us. Humans are really what we measure against. So it puts an upper bound. They put an upper bound on the performance of our system. And there is also the issue of privacy. We definitely don't want to have humans listen to things that we might actually want machines to transcribe and do a good job at transcribing. There is the issue of scale. We receive right now about 2 years of data, 2 years worth of data every single day, and that in 27 languages. We can't even imagine trying to transcribe all that data. And so how do we leverage it if we don't have humans annotating it? That's the fundamental issue that we're facing. So Fred Jelinek is a famous researcher in speech recognition. He used to say that every time he fired a linguist, performance would improve. So I'm just trying to take it a little step beyond. The key to make it work is this very simple idea. In speech recognition, as I say, we have those two models. We have the acoustic model and the language model. And they work in tandem. They combine together to produce your results. And they sort of compensate for each other's deficiencies. Right? So the classical setup that we have is we have the truth that's determined by a human transcriber. We have our system, and we compare that system to the human to evaluate how well we're doing and to try to push the system towards the performance of a human transcriber. If we don't have a human in the loop, we're out of luck. We don't have anything that we can measure against. We can't improve. But we can cheat. We can cheat by taking parts of our system and artificially weakening it and making it harder on that piece of the system to work. So what's going to happen? We have now a system that's worse than the best system ever we can have, and we're trying to push the system and push the rest. So if for example, here I'm making the language model worse, and we're going to try to make the acoustic model compensate for this deficiency. So as a result, hopefully, the acoustic model is going to get better. Now we can switch the roles, make it harder for the acoustic model to work. The language model will improve. Now we have a better acoustic model, a better language model. We can combine them together. We have a better system overall. We can iterate and keep going. So you'll notice there has been no human involvement, whether in training or in evaluation or in any of the steps that we do to actually run the machine learning pipeline. This is in general in an idea around unsupervised training. Unsupervised training itself is not something new. It's something that researchers have been doing for a long time. What's really new and really exciting to us is that we're not only training in a completely unsupervised fashion. We have a complete development cycle that doesn't involve any human supervision, any human interaction, and as a result, it can scale to a much larger amount of data and much larger systems. The hope there is that by removing this asymptote, by removing this ceiling that we can never reach, we'll finally maybe be able to reach human level performance. And with that, I'll just give the floor to Remco, who will talk about OCR.
Thank you. Thank you, Vincent. Okay. Google's mission is to organize the world's information and make it universally accessible and useful. And that includes, of course, books. But unfortunately, OCR is not available for all languages, or it's not good enough. But we feel we're in a good position to basically build our own system. Now, OCR hasn't been heavily researched as it has been in the past, but other areas are. And for example, we want to take advantage of the developments in speech recognition and in machine translation. And of course, we have a massive amount of data that we also want to use. Our initial goal is to focus on Google Books, but ultimately we want to be able to do universal OCR, meaning that you give it any image with text and will recognize the text. And the goal of the team is basically to create the world's best OCR for all scripts and languages. Now, that sounds easy, right? Well, maybe not. Actually, OCR is a non-trivial task. There's many, of course, scripts and languages, but also fonts and styles and sizes. Some languages have a really large number of characters. Other languages, go from right to left, and you can even have like left to right within the same sentence. Then there's languages that have characters that look very similar. And of course, I'm not even talking about the layout problem. In fact, what I'm talking about here and what we're focusing on is just recognizing an image that has a single line of text. So what's the approach? Well, first of all, we're starting from scratch. We're not taking an existing system and adapting it or trying to improve it. We're starting from the ground up. And the basic idea is to use multiple models, including hidden Markov models, language models, and template-based models, and combine it in the log linear space. Now, Vincent didn't mention it, but his acoustic models are hidden Markov models. And he also mentioned that he's using a language model. And in fact, there's a lot of teams out there that simply use their speech recognizer to do OCR. Now, we want to be able to make different design decisions for our system, so we're not. But it doesn't mean that we cannot take advantage of the technologies that the speech team is developing. So for example, the technique that Vincent just talked about in terms of doing the unsupervised discriminative training, we can use that too. And for example, on the language model side, the machine translation guys, they use the massively distributed language models, and we want to be able to use that too. And of course, the whole system is going to be data-driven. Now, talking about data, we're actually in a very nice position for OCR because we can generate our own training data. And they can't do that for speech, for example. We can print text on paper and then scan it back in. And voila, we have training data. So that's very nice. But in fact, what you can also do is just simply create images from text directly and then distort it a little bit to make it look like it was scanned. And then, of course, the sky's the limit in terms of what you can do. But that data is still not going to be as good as data from actual books. But if you can use the synthetic data to create a system that is good enough, then you can take it from there and do unsupervised training with it. So the idea is basically you take text, create synthetic data, train your system, and it will pop out a model. And then, assuming that the model is good enough, use that model and scans from real books to improve the system. So that's very nice. So how have we been doing? Well, we've been making good progress. We're still a very young team. This slide shows the character error rate as a function of time. And the timeline here is starting in June of this year. The task here is recognizing text lines from a variety of books, which means there's a variety of font sizes and fonts, etc. There's two lines, one for Chinese and one for English. Now there's a nice curve going down. But of course, the cynical view is that if you start up with error rates high enough, then it's easy enough to make progress, which is very true. But what is nice, or for English, we're now actually low enough that we've sort of reached the state-of-the-art performance, at least for this test set. But as you can see, for Chinese, we still have a long way to go. Now, I want to show an example. This is Thai. And the top line is an image from an actual Thai book, and then there's two lines below it that are recognition results. One, which is called Other, is from a commercial OCR system, and the lower one is from Google. Now, go find me the difference. It's actually not that easy. Certainly if you don't know Thai. But maybe you found them. There are 5 differences where the other system and our system differ. And let's zoom in on one difference. So here it is. Now, you can sort of see that that little circle in the middle of the arc is sort of attached to the arc differently. And you can sort of imagine that if you look at the image part, that if you get a little bit more noise, that it will be impossible to tell the difference. Now, if you actually look at these 4 cases, or 5 cases where there's a difference, then 4 out of the 5 we do better. Now, of course, this is a very carefully selected example. But fortunately, there's more of these kind of examples. But there's also examples where we completely fall apart. But I didn't think that that would impress you. But the thing is, all kidding aside, there's actually a much bigger story here. And that is that this Thai system we built in approximately 12 hours from scratch. So I think that's very nice. So what did we do? Well, first we downloaded 25 megabytes of Thai text from Wikisource. And then we just simply fed it into the training pipeline. And out popped the model that gave the result that I just showed. The training pipeline involves training a language model from the text, training or generating artificial data from the text, then training the optical models from that synthetic data, and then finally tuning the system automatically on some held data. So, and that's basically it. There's no real human involvement at all. I mean, you basically have to download the data and you feed it back in, and then that's it. Now, this does not give you a particularly good system. It's suboptimal. It has a very small language model. It has very small optical models. And we use very few fonts because I didn't want to spend the time searching for a lot of Thai fonts. But that's actually very important to have a good variety of fonts because the system needs to see sort of a critical mass of a variety to be able to generalize well. We didn't use any unsupervised training, and we don't actually have any transcribed data because, of course, that requires humans. And so we don't actually know how well the system works. But, you saw the example, and it's not too bad. So what are we currently working on? Well, synthetic training data, we just really got it to work. But now there's so many things that we can do, and we're still exploring that realm. We're working on unsupervised and discriminative training, discriminative feature extraction. We had somebody work on deep belief networks, and he got some promising results. And we want to scale to more languages. Currently, we're working on 5 languages: Arabic, English, Hindi, Russian, and Chinese. But we want to scale to 25 languages. And that will basically ensure that we cannot optimize for any particular language because there's just too many of them. So that will ensure that we remain sort of language independent. So to summarize, OCR is a non-trivial problem, and it has not really been solved, at least not in general. We can take advantage of the latest technologies coming out of speech and machine translation. We can generate our own training data and then use that in conjunction with unsupervised data to actually take advantage of the huge amounts of scanned books that we have. We're still a young project, but we've been making great progress. And for English, we've sort of reached state-of-the-art performance. But there's still a lot of work to do. So that finishes my talk. Now, next is going to be some cool demos from my colleagues, Jay and Doug. And they need a little bit of time to set up. So please stand by. Thank you.
All right, I'm Jay Yagnik. I'm going to be talking about machine perception, and particularly with emphasis on what large data sets can do for us. So let me just define what I mean by machine perception here. When we talk about machine perception, as a high level, I'm talking about audiovisual analysis. So we do computer vision, machine hearing, video content analysis, and some cool work on learning models with inspiration from actual biological visual models. At a high level, the technical problems spanning the space of machine perception can be divided into 3 sort of main buckets. The first one, which we call semantic interpretation, is basically coming up with knowledge the way humans understand knowledge. Right? So when you're given an image, it's a describing image in a way that a human can understand. That would be semantic interpretation. The other ones are when you have an image, video, or a piece of media, we'd like to find stuff that is similar to it. And you'll see more demos of this later from Doug. And the third one is when you have lots of data, can you actually create new images, video, audio that would sound cool or look good in a given context. For the remainder of the talk, I'm actually going to just focus on semantic interpretation. So we'll be taking some case studies which are around problems that require us to generate human-level knowledge. But before I do that, let me first pitch what scale I'm talking about. So every time I say large scale, right? Here are examples of some public numbers on what we mean by scale. So YouTube gets about 48 hours of new video uploaded to it every minute. So for the 10 minutes that I'm going to talk, that's 20 days worth of video, right? Let me emphasize on that more. In a week, that's equivalent of 240,000 full-length feature films, right? In about a day, we get 8 years of video, right? So you do the math and pitch these numbers with relative to other large numbers that we would have known. Like we get more video on YouTube in a month than the 3 major media houses in the US have published in the last 60 years, right? And so we're talking about writing algorithms that are going to work on this scale and hopefully mine knowledge that we otherwise could not do, right? And this fits in very well with our mission, which is organize all of world's information and make it universally accessible. My favorite quote from there is that most of the world's data lives in pixels today, right? How much information is there in pixels? That's a function of how well we can do our job in parsing those pixels, right? Okay, so I'll be talking about 3 case studies along with related demos about 2 main themes, right? One is what I call information fusion, is when you have data sitting in separate corpora, and if you get smart about how you integrate information across these corpora, you can extract a whole lot of knowledge. And we'll take case studies of celebrity recognition and place recognition from there. And then part 2, I will talk about how you can leverage crowds tagging stuff to learn knowledge also. So going to the first piece, let's try this crazy experiment. I go through all the web pages that are out there and pick someone up from the natural language processing line and say, give me a good named entity parser, right? So a parser that will tell me this text phrase looks like it might be a person name, right? And I run that over all the web pages I have access to, and I start counting how many times the text phrase came up and was called that it might be a person name. After I'm done counting, right, I have some measure of reliability. Something that occurs 50 million times is probably likely. So then I take these phrases and I go to image search and I query image search with those phrases, right? And I get, let's say, a few thousand results back, right? The phrase might not have been a person name. All the images that come back might not be from this person, but I have some notion of relevant knowledge that is building up here, right? Then I can take this giant list of people names and images that came back and do some fancy machine learning that would filter out noise and get me good discriminative model creation. And in the end, I can learn automatically models for all of these people without ever having to specify that this is a person and this is how they look like, right? And later, when a new video comes up on YouTube, I can run these models, and without having to enter any text, I can basically say, I know the people here because they appear so frequently on the web, and I have these images that they appear with, and I can reliably identify that this is the person and this is how they look like. And so here's an example of an actual system. So what I'm showing is the last piece here, where assume this was a video uploaded on YouTube, and this is actually a collection of YouTube videos that I put together, where the system is run.
What to be said when they look at the record?
Enter a child how to read. I know the human being and fish can coexist peacefully. I think we ought to raise the age at which juveniles can have a gun.
Mes chers compatriotes, les apprentis sortent.
Sure. To advance to.
If I was going to the park to play with my friends, I dribble my ball there. If my mom sent me to the store, I take my ball with me. All
changing experience. I saw some amazing, beautiful, invigorating.
What's the difference?
This is Martin Scorsese at the top of his game.
So again, remember, the fact that these are people is completely automatically discovered.
Kick-ass Scorsese moment.
New on-screen image.
And if you read carefully, the name said James Bond. Well, that's the side effect of data, right? Right? So if this is not cool enough, we can take it a step further. And now that we have a reliable system that can tag this on video, people talk in a video, right? And so every time I have a good belief that it was James Bond speaking, right? And I see lips moving, I see the head tracked correctly, and then I can record the audio and say, let me try and find patterns in the audio that might be typical of James Bond, right? And using this system, I can now completely automatically bootstrap a training process for how people sound like, right? So I started from what was written web pages on text. I went through image search. I went to video. And now I can build a model for how people sound like. And we actually did that. And then you can, it's an independent source of information. The errors are uncorrelated. And then you can come back and fuse both the models and show that the end product is better than either one of the two individually, right? So it's an example of how powerful this concept of information fusion can be when you are sitting on multiple types of data that have plausible relationships between themselves. And the concept can actually be extended. It's not specific to people or celebrities. We can do it for places. So using the same principle, we built a landmark recognition engine for more than 50,000 landmarks in the world, covering more than 100 countries. Again, completely automatically. No one specifies what a landmark might look like. What we look for is web pages that seem like they're talking about tourism-related stuff, right? So we look at that. We look at pictures that are uploaded to us and marked as public, which are from these places with GPS tags. We basically put them together. For all the text phrases that we mine from the tourist-sounding articles, we follow the same principle. We query image search and gather, a few thousand images. And we have these photo sharing websites like our website Panoramio or Picasa Public Albums, right? So we put these sources together, then run some fancy image matching to say, for all these images, I really know that this part of the image is common with that part of the image, and even we can do that reliably even when there is 3D angle rotation. So after doing all of that, I can filter out what are noisy hits and come up with true plausible models for what these famous places are, right? And so using the same principle very easily, we just switched our matching model from matching faces to matching places, right? And using the same principle, we automatically built this very large-scale landmark recognition engine. So that was information fusion. Another very powerful source of data that we are on is crowdsourcing, right? So on a property like YouTube, and let me repeat Francis' question. How many of you have used YouTube? Yes. So, people give us a lot of information on YouTube. People tag videos, they do all kinds of activities, they leave comments, right? You can imagine that body of work put together should give us a lot of information to create some true knowledge out of it. And so we attempted to do that in the first level using crowdsourced tags as a source of information. So for, if a tag like car crash has come up 5,000 times on YouTube videos, it probably means something. And given the fact that the tag has come from different people, it means it talks about a concept that people seem to agree on, right? And so we do the following simple experiment. We look for all tags that have some minimum number of videos with that tag. We extract some general sets of computer vision-based features, both audio and visual, from the video. And then we set up a machine learning problem to predict the tag given those features, right? And so a pretty simple, straightforward thing to do. And we then come in and say that now that I'm looking at a really, really large space of tags, let me see if I can recover some real-world compositionality from here. And so we do the following experiment. We ask these classifiers to train against the tag versus not the tag, and then say how many of these classifiers were better than a certain measure of accuracy, right? And so we call them, the good classifiers versus the not good classifiers. So let's say we tried with just 10,000 classifiers, and let's say 1,000 of them turned out to be good, right? So what we do is we take those 1,000 classifiers and say, I'm now going to add them to my knowledge base, which means I'm going to take the results of those classifiers now as features. And I'm going to ask the same question again. can we now learn the other classifiers correctly, given that we have the original features and these 1,000 classifiers? So if I ask this question, it turns out that layer over layer, we can learn 20 to 30% more classifiers using this process. And we can learn this only because concepts depend on other concepts, right? And we actually trained up a 5-layer model. And we went to layer 5 and inspected, why is it that some tags were only learned in layer 5? And we inspected some music genres to test out. And it turned out that the iteration 5 music genres were what was considered by Wikipedia as complex or more evolved music genres. And the sources of inspiration for those genres happen to have good correlation with our dependence tree in this layered model. Right? There's another example of a place where we recover some information that is close to how we think of state of the world. And another peculiarity of human learning is that as we learn more, it gets easier to learn. We need fewer examples. So we showed here that after you trained all these tags, if you take this collective tag space as a feature space, then with 10% of training data, you can learn a better classifier than you could with the original low-level feature space. Right? And so we're basically moving up in representation from low-level audiovisual features to these semantic features. Right? And again, learned completely automatically. Humans were telling us that these are dimensions of knowledge that we care about by the fact that we tag them frequently, right? And the fact that we go into that space, we can do this on a completely unrelated problem. So this graph basically shows a binary classification performance on a problem that was not part of the tag learning setup that we originally started with. And here's a little demo. So this is basically some training dump of intermediate results. And I believe I am on the tag car crash right now. Right. And so you see things like, say goodbye to the world you thought you lived in, to the world you thought. And let's see. Sure, animation is easy. Let's do airplanes. Oh, awesome. Well, trust me, airplanes work. I've seen that. All right, I'm not going to try and. Right. What we can also do after we get these basic tag classifiers is to say that the very fact that we created this dependency tree and we exploited this inherent correlation between tags, we can say that not all tags are independent, right? Which means there is some structure to the space of tags. And what we can do is, once we have the classifiers for these tags, we can measure the correlation between these classifiers as a data-driven way of measuring how correlated the original tag spaces are, right? And we can essentially use this process to cluster tags and automatically come up with higher-level concepts, right? And so we have done this in several iterations. If you go to youtube.com/browse, you're going to see a taxonomy of videos that you can browse by. And many of those categories were automatically learned bottom-up through this clustering of tags. And here are a few snapshots of what that looks like. So in summary, I basically talked about two ways of exploring information when you have very, very large data sets in order to create knowledge. One was information fusion, where you go across multiple modalities of data. And second is crowdsourcing, where you use humans giving you independent knowledge to create a very large knowledge base. And that's about it. Thank you.
Hi, my name is Douglas Eck, and if you haven't figured out there's a theme here, I'm also from Google. Got the last 10 minutes here for you. We get to talk about a little bit of music. And more specifically, well, let me bring this up full screen. Sorry about that. We're going to look at the problem, the specific problem of starting off with an audio waveform and moving through acoustic features into some space where we can pull out some musical meaning. So the slide that I put up here shows some waveform, some wave file being pushed through some features that I'll describe in a minute. And then from those features, we do some machine learning and come up with a probability that this original segment was reggae, or that it's good for jogging, or that it contained a kazoo. And if you followed the theme of what the previous speakers have mentioned, it probably goes without saying that we do this with lots and lots of audio data, and that we train over lots of words. So we're looking at large-scale learning. But what I want to do for you now, as opposed to walk you through a specific blueprint of the system, I want to try to give you some intuitions of what it means to move from raw audio through some acoustic features and towards some learned features. So I'm going to play some audio demos for you. The main goal here, actually, if you want to take home the research message, is we're doing the best we can to pull out musically related features from audio in a way that's tractable. And we're using some nice machine learning techniques. Luckily, Sami Benjo, for those of you who saw Sami's talk this morning, it was this morning, right? Yeah. We're working with Sami and using some of the same techniques at different parts of our pipeline. So you've already seen some of the machine learning techniques. I don't need to talk about that. But what I want to talk about here, first, my first demo, is just to talk about some simple audio feature extraction. And there are two pretty pictures up here, the one on the left and the one on the right. And most of these features are drawn from the speech recognition community, in fact. So we have spectra. Let's see if this laser works. Does that do anything? Is that a laser? There it is. We have spectral content here. We have something called cepstral content, or MFCCs, for those of you who do signal processing. And then we have some autocorrelation features. So column are the features, and time evolves from left to right. So the fun part here is to listen to these things. So let's see if we can make this work. I'm in full screen mode, sorry. All right. Where's my video? That's strange. Is it sitting behind here? Let me quit. I think it's because I switched. We're having demo problems today. I think it's because I switched video modes here. Let me pull this up a second time. I played these over and over all day compulsively, making sure they'd work. Of course I have. Yeah, there it is. Okay. So I won't spend too much time on this, but it's hard to see on the screen, but there's a little red line that's moving from left to right. Okay, and what you're hearing is the track Pink Floyd Money. And can you hear that? Okay. So as we're moving through time, what you might say is that we've managed to take a hard problem, which is audio signal processing, and reduce it to an even harder problem, which is image signal processing. Okay. And what I wanted to point out in this demo is I'm going to skip forward a little bit, and I want you to focus on this bottom part here. These bands roughly correlate with rhythm, with the bass tempo and then harmonics of the tempo. So as these bands move up, the track gets slower and slower, and as these bands would move down, the track gets faster. So what we would predict here, if we were using these as training features, is that something happens here radically with the rhythm of the song, and that it gets quite a bit faster. So I'm going to jump forward here. And so what we have is a saxophone solo happening, which incidentally shows up consistently in these features up here, which correspond to timbre. And as soon as this sax solo finishes, we're going to have a quite a bit faster tempo shift here. The point being, we can pull out of, even using sort of standard speech recognition features and adding some simple rhythmic features, we can pull out quite a bit of structure from audio that uncovers the underlying musicality in the signal. And to really help, I think, is to see, here's a waltz, okay? You'll notice that, let's just play a little bit of this. This is a piano. You might have to bring the volume up on this a little bit. I might need to hit play, thank you. One thing we see is there's no stable tempo at the bottom. It's very difficult to tap your fingers with a rubato piano piece. And so our bottom features here look very, very different. There's none of these bandings that we see. And there's also much less full spectral content and different looking cepstral content. Is it going to reset? No, we're OK. OK, so where do we go from here? Here, I think things get fun. I try to give you a basic idea that we have some underlying feature spaces that we can extract from audio that will uncover a lot of the regularities that aren't there in the waveform itself. It should go without saying. Well, let me continue on this. So where I want to go from here now is to talk briefly about sparsification. That is, we want to move from a dense feature space into a sparse one for various reasons having to do with machine learning and wanting to use linear models. So now what we'll do is use a very simple k-means clustering algorithm. So we're going to look for k-means in a multimodal space. And we're going to take as our space one of our acoustic features. And it turns out if we take a histogram over these cluster indices, it gives us a nice sparse code for doing learning downstream. But it's, I think, really fun to listen to the audio samples near a cluster. So this is an even more fun demo, if you ask me. So what we're going to do is have a look at OK, it takes some explaining. Imagine we take 20,000 or 30,000 tracks of audio. And we take some acoustic features, in this case, some MFCCs, and we run k-means, extracting something like 3,000 different means. And then we find one of the means, which is a cluster in the space of MFCCs, and we ask ourselves, well, what does it sound like to listen to that cluster? So we simply dive back down into our audio, and going back through 5-second segments in all 30,000 songs, we pull out the closest match to one of our centroids. And I've listened to hundreds of these and pulled out some ones that sound fun. So what we'll hear are some centroids, if you will, some tiny little musical words that seem to sound like maybe some choral singing, some piano, and some strange electronic sounds. So that's choral. Piano.
Later.
A third centroid that clustered some electronic sounds, kind of noise sounds. Okay, the point of that demo is to show you that inside of even relatively simple features, there's an underlying space that's quite complex and gives rise to a vocabulary of thousands of relatively interesting sonic words, if you will. So then the question is, how do we get from these sort of acoustic elements to something that sounds more like music? And to do that, we bring our slide back up. To do that, I really don't like jumping back and forth, but there's not much I can do about it. Let's just do that. Oh, I did quit, didn't I? Well, that's terrible. Wait a minute. And so what we'll do here is take these acoustic features and use supervised machine learning. So we're going to take this feature space, having been sparsified, and we're going to move it through a machine learning algorithm that will try to learn some of the regularities and take these underlying acoustic sounds and map them onto musical classes. Okay. I'm not going to talk about the machine learning again because Sammy talked about a lot of this morning. Instead, I'm going to rely on a demo. So what I'm going to do is ask you to think about the vocabularies that were available to us in this sparse representation that we just heard, and they have they have a lot of surface similarity in terms of acoustics, but they don't have the ability to, without some machine learning and some remapping, to actually cover the acoustic variance of an interesting class. So, for example, let me play reggae for you. What now we're going to take is a model trained on positive examples of reggae, mapping these acoustic features onto a classifier. And then we've taken out-of-sample data and pulled the nearest, sort of the hottest, the best match for reggae. So, of course, I am. Pay attention, if you will, to the fact I hope you'll agree that these all sound like reggae, but the actual acoustic similarity becomes weaker and weaker as we move towards having a kind of musical similarity that's based on something as high level as a genre.
And you know it's true.
Okay, that's enough. I want to make sure I have time for the last slide here. So where are we going with this? I think, let's see. In terms of research in our group, we're spending a lot of time looking at new audio features. So the examples I gave you were relatively simple features. That is, I have 5 minutes? OK, good. Perfect. Awesome. That was 5 minutes over. So we're looking at new audio features, and specifically we're looking very closely at what realistic auditory pathway models can do for us. So if you look at these bottom plots, looking at paying less attention to spectral-based signal processing models that are popular in speech recognition, and looking more closely at realistic cochlear models that use filter banks and stabilization, and also in following using vector quantization and sparse features, as I just mentioned. And we've numerically shown that outperforms some of these other features. But it's a relatively complex story to tell. So in a 10-minute overview talk, I didn't want to fall into the trying to explain what these pathway models are doing. And we've also been looking at a very, very hard problem. How can we pull more long time scale structure into our research? For those of you that might think of speech recognition by analogy, we are looking very closely at very short time scale structure to make predictions about things like genre and instrument and artist. But it amounts to taking music and cutting it up into 500 millisecond chunks, putting those chunks in a bag and shaking it up. Okay, so we're not paying enough attention to long time scale structure. And it turns out to be really hard to pay attention to long time scale structure because we don't have anything like a language model. We don't know really enough about how music fits together in long time scale to build tractable models that don't explode as you move through sort of all possible combinations of short time scale segments. So this is a really hard problem, and it's a deep problem. How do we do music? How do kids handle music? How do they track things in time? How do adults do music? And how can we get machines to do the same? So finally, and the last demo that I'll do, is to begin with, why care about audio? So some of you may be asking that question. Behind this is a desire to build tools for music recommendation and music discovery. And I'll give you a demo of that in a moment. And you could ask yourself, why not just use collaborative filtering? Why is music special? And as it turns out, I think you can make a convincing case that the way people use music is special. We listen to the same tracks over and over again. We have favorite artists. We have favorite songs. And we tend to recombine those songs in sequences, whether it be listening to a whole album or building a playlist. And the space of sequences of songs is immense. There are an order of magnitude more songs out there than movies already. And then when you start sequencing tracks into playlists and into bits of albums and into dinner party music and into music for jogging, the space is so immense that if you want to use a standard kind of collaborative filtering approach where you say John likes X, Mary likes X, Mary likes Y, John will probably like Y, you find that you have a problem that you can write down in the same way as a standard sort of books collaborative filtering problem, but that the sparsity of the data becomes a problem. Furthermore, and related, if you think about what it means to use a particular track, I guess this is a concrete example. Think of the track Taxman from the album Revolver. That might show up on a playlist because you want it for jogging. That might show up on a playlist because it's dinner party music. Maybe you're listening to a Beatles fest. Maybe you're listening to the album Revolver. If we have 2 or 3 bits of information, if we're going to do good playlisting and offer good discovery, we'd better manage to be sensitive to that. OK, so my last demo, and I will make it in on time. I'm going to give you a last demo of the work that we're doing that highlights the audio component of the work. We are going to talk about making a playlist, okay? And we're going to talk about making a playlist from a seed. So the seed artist in this case is U2. And the first thing I'll play for you is a few seconds of the similar artists that would be brought up and some randomly chosen tracks, popular tracks by those artists, to say this is kind of what a standard collaborative filter would do if you said, I like U2, give me some more music. I'll make it. So we start with U2. This was done on a relatively small music collection, The Smiths. You can argue about that. U2 comes to New Order or Joy Division or something like that. In any case, a sequence of sort of kind of artist level similarity based upon the original seed track, the era of the track. Now we're going to talk about something I think is more interesting. What if we started with 2 different songs by the same artist, and we wanted to make a playlist from there? Okay, our metadata on the song level is pretty sparse, so we're more or less going to rely on artist level metadata for looking at similarity. We're going to have to be thinking about the difference in the way the songs sound. So what I'll play for you first is a playlist that was made based upon a very laid-back track, and I'll compare that to a playlist that was made based on a really upbeat track that's paying attention to the sonic similarities between these songs and other songs, and then I'm done.
When I'm feeling low down.
Okay, so that's the laid-back one, and here's the upbeat one. Same artist similarity. And in fact, those were drawn from the same music collection. These were drawn from a music collection that we were using for testing for Google Music Beta for Google, and it's the playlisting functionality for that was built by us. So I'm out of time, and I hope that I gave you guys a few fun music demos to listen to. The take-home is that I think we're moving towards trying to have some uncanny, interesting playlisting and discovery tools built around audio. You can see I left a blog posting that you can look at if you want more citations. And I think now I can stop being between you and drinks and dinner. Thanks.
So we'll now have the speakers come up for questions.
Hi, Mike McAlpine from Princeton. I'm not sure that this is something that Google would be interested in, but I'm just interested in it, which is, can you ever perfectly unmix a song? Like, for example, a song from the 60s where the tracks are not widely available, the individual tracks?
Not perfectly, but source separation is a nice problem. And there's been a lot of success in doing source separation for music. It's expensive to do. A lot of people are spending time on it. So the answer is yes, but not perfectly. Thanks. Not a very interesting answer, sorry.
Hi, Tim Barkoltz from ExxonMobil. I watched Jeopardy earlier this year and saw Watson beat the humans quite convincingly, and read the book about it. I think it talked about Google Translate there. What is your opinion of that Jeopardy and Watson? Is that just a one-off thing? Is that the wave of the future? Was that child's play compared to what you can do? I mean, what did you think?
I read shortly after the Watson performance an article where people actually took the questions that were asked that were posed to Watson and put them in the Google search box. And if you consider a correct answer to be an answer that shows up on the Google top first page, then we did about as well as Watson, according to that website. Now the real trick is, how do we make it the first answer? And how do we make that answer semantically relevant, something that you can actually process and that you can actually use for something more actionable? And that's a really interesting area of research, providing these kinds of answers beyond just search links.
But you wasn't identified Toronto as being a U.S. city.
You got that question wrong. You have to ask Google that.
Okay, I will follow on. Haiyong Wang from Texas A&M. It's amazing, so many experts in front of us. We were just searching online and search for topics, and you were in front of us.
I think we would beat Watson, the five of us together.
Yeah, the question first is for the Google Translate. Actually, I happen to use it to translate some of like my paragraph into certain different language and try to fit through. One problem I had was when I run into technical words. For example, let me use the word twin. Twin in material science understand as a special interface between two grains, which looks very much similar to each other. So we call twin interface. But when I put that particular words into a whole paragraph, then the translate comes out as a twin baby. So into other words, into other language. So I just want to see, that particular words has to be set in a thing, so describe a different meaning of that. So what's the Google?
I'll add that right after that into the dictionary. So in general, to take into account the context of words in order to make a good translation, that's a key challenge in translation. And if you look at where technology is at this point, then if the context is very local, then with those n-gram models and very large amounts of data, we can actually make typically very good decisions. But if the context kind of is more long distance, that it would be necessary to kind of figure out that this is now something which is in a specific domain, right? In a specific subdomain, that word is used very, very differently. Then this is a harder problem. And so this is an active research area to take into account, to make long-distance inferences, to infer from the context.
You have some sub-columns. This is for technical people. This is for like a standard, just common language. This is for maybe medical application. Maybe you have some sub-columns people can select on. Then we can define the word.
Right. So this is active research. So in similar ways here, the idea would be, for many of those things that we're trying to do, there is to do a lot of things that are unsupervised, that we wouldn't require these kind of explicit annotation, because then we'd have to have all our training data annotated by domain. But to do that in an unsupervised fashion, that we basically can infer that in all these areas this term gets translated like this, and in all these areas it gets translated like that. But machine translation is a hard problem, and I think basically with a lot of data and applying this data-intensive approach, a lot of progress has been made, but there's still a lot of progress to be made in the future.
Okay. Actually, one last question. I know I take many. I think many people also have a similar experience when you type in. I mean, this is for all of you. Actually, when I type Google, I search for something. When I type in words in different sequence, or type in actually the same question, but ask in a different way, but turns out the answers are very different, or the results are very different. Do you have any comments or suggestions on, what's the most effective way we can find, how do I describe, shorter sentences, or maybe few words, or,
The answer is it shouldn't be your problem. It should be ours. We should be doing a better job at understanding what you're asking for. Right, and you shouldn't have to play tricks with the system to actually make it work better. It should be completely natural. So yeah, it's a tough problem.
Okay. Thanks a lot.
My question, Sam Geckler from Cummins. I have interest in optical character recognition as it pertains to scanning old texts. So for ancient texts, how good does it have to be before you then would represent it as this is what was written?
That's a good question. I suppose that, if there's no relevant fonts available anymore, then it might be hard. But you can, of course, start with scanned books, old scanned books, and annotate them by humans, and then use that as your seed and go from there, basically. So, in fact, somebody's working on like ancient Greek to try to do OCR for that. So there's a way. I mean, we might not be able to do it automatically, but that's fine too, right? I mean, in speech, they don't start from text or anything like that either. They do a big data collection effort where they have speech annotated by humans and then go from there. And we can do the same thing. So in terms of technology, I don't think there's any problem. We should be able to do it. Does that answer your question?
I just want to know how good you have it be before you would be willing to represent this. This is what Google's representation is for this ancient text.
I think that if we actually going to show it to you, then it has to be really good. But if it's just for searching, then you wouldn't know, right? You just won't find a term that you're looking for.
Have you thought about what that means as an organization?
I don't know any numbers. I mean, if that's what you're looking for in terms of like accuracy, or maybe functions. I don't know.
So I guess it's just for different applications there would be different quality thresholds. So I guess I can answer that for machine translation, and it's something where we went through different iterations. So machine translation, people that tried machine translation 10 years ago on the web, and said, "Oh, this is all pretty bad," and so we're unhappy with the results and thought it not to be very useful. And then over time, basically machine translation improved, and with those data-intensive techniques, that now very many people use machine translation and are very happy with it. But what we also see now for languages for which there was no machine translation available before, that when we make it now available, actually quite low quality still gets a large amount of usage, and because there is a fundamental need there to get access to that information. So where we, over time, we basically have this quality bar where we said, right, we only want to make it available with that quality bar. And what kind of was arbitrarily set, we just said, right, this is what we feel is good enough. And over time, we're actually lowering that because we noticed people want machine translation for getting access to information and data. And right, if you have no way to get to that information, or you have crummy empty, then you would take that. So I think also here it will depend on various different things, and it depends on the application where it might not be useful for some applications, but it would be very useful for search or other things. I don't think there's a clear answer there.
I have a product suggestion, or maybe you already have it and I have not known it. So I travel a lot internationally. Is there an app on Android where I can take a picture with my phone of a street sign in a foreign language and it will translate it for me?
There is. So you download the Google Goggles application on Android, and you can do exactly that. You take a picture, and it basically gets sent to the server. The text gets OCR'd, recognized. It gets translated, and you see back the information. And it has all kinds of other image kind of things. It's especially good for wine bottles to figure out what the wine is. So you can look like a wine expert in the restaurant if you secretly do that. But there's also this translate integration. I think it's another one for translation. I think the exciting thing now, for normal text translation on the web, it gets very heavily used. And basically people are using that on a daily basis. But then these other kind of places where you run into a language barrier, that's when you communicate to people, when you talk to people, or then when you're just faced with a document which you don't even have online to put in. If you go to Japan and you don't know Japanese, you have a hard time putting the text into Google Translate. So then those other kind of technologies, they all combine together, and then at some point the language barrier will be much less of an issue.
Go ahead. So these are, first I want to say these are just amazing results. The performance you showed just now a few years ago would be deemed impossible by AI researchers, and now you're just showing it works. So it's fantastic. I think the singularity is near. That's the conclusion. The question I have is taking it to the next level, and by that I mean synthesis. So everything you're showing is about analysis, taking stuff that humans have generated and understanding it. Can you take this and now generate new content? For example, can you generate new songs, new music that is similar to existing music but different? Can you generate new images that are similar to existing ones but more beautiful or more interesting, and so forth? So moving from analysis to generating content, is that, I think there are some similarities, some principles that could be used, and maybe that's the next thing.
So in my talk, if you remember, I talked about three big areas we work in. The first was semantic interpretation, which is what I focused on. The other two were large-scale matching and synthesis. Synthesis was indeed the third area. And the kind of use cases you describe are pretty high level. Synthesis is actually required from ground up, right? So any place where you collect imagery, where the collection process has problems, right? You could imagine synthesis coming in there to complete the process for you, right? So there are quite a few places where we actually work on synthesis in that context.
I guess I just had it's amazing what you guys are doing, but most of what is focused on is trying to basically make the perfect human, right? You're reading flawed data because it's put on by people who are relatively flawed and trying to get the right answer every time. Well, there's some cases like for marketing surveys and stuff, maybe people would want to go online and say, okay, what is a person going to think of this product? That you don't want, there's no right answer. Is there work being done on that of like trying to design more like a human that would be flawed but in nature rather than giving a perfect answer because people make unrational decisions?
We don't have to work really hard on being flawed.
Actually, I could comment to that in an indirect way. Some of the things that our group is trying to do, there's no right answer in the first place. So a number of queries, it's possible to come back with a nice ranking of what you think the right answer should be, not always. But for example, even take the simple idea of building a good playlist. I don't know, I think I know have some ideas, but I mean, it's not really clear. I'm very interested in caring a lot about what people want in the first place, whether rational or not, and trying to model some of that, I guess, irrationality, if you want to put it that way.
So we're also doing things like sentiment analysis for reviews or so, where then you basically see, right, what people would think about a restaurant and the food in a certain place, and that aggregates kind of the rationality or irrationality that people have. If you look there at different restaurants, you might have then a very different opinion, but there you see kind of the average opinion that the web is having or people are having there. So in that respect, things like that get modeled too and are then exposed back to the world.
Evgeny Gavrilovich, Yao Research. I have a question about OCR. You mentioned you are using language models and you're doing OCR for books which span hundreds of years. I wonder if you build language models for different periods of time, because language has evolved over 500 years. Mouse and keyboard 100 years ago meant a furry animal, probably a piano, not computer parts today. So I wonder if you model language change in
right. I mean, that's definitely possible. And generally, we probably have like a two-pass approach where you have some maybe language or time period independent model that you first try to do a first pass to get some idea, and then in the second pass you might use like an area-specific model or a book-specific model or whatever it is to do a rescoring and get a better result. So what you're talking about, and I mean certain languages, the spelling completely changes and stuff like that. So you would definitely need to do that.
I just wonder at which resolution do you need to model language change? At which resolution do you need to model language change? Do you need to build a new model for every year in the past, every decade?
That's a good question, but I suppose you would do it on on an unsupervised way. So you wouldn't decide in advance like how many chunks there would be. That would just depend on the language.
Sure, I was just interested what your findings are.
So I guess one more general answer there is, and probably we didn't go to that too much. So for this specific case, I guess it's also a research question that's still open to be figured out. But one thing that kind of also occurs as a pattern for a lot of the work that we do, it seems that simple models with very large amounts of data often do a very good job, and finer-grained distinctions and complexities in the models are sometimes not necessary. So the same thing, basically, that you referred to for OCR, for it's spanning a very long time frame. For machine translation, you have a similar issue where, conceptually, right, there are all these different domains, and so ideally you would want to fragment your training data in all these different domains, and it just turns out to be very, very hard to do. That one of the best things, and in some sense it's great from system development, seems to be at this point, given where the models are at this point, to just throw all the data together and build very long history models where you have n-grams of a long size, and you have a very large amount of data you can still remember then or estimate those reliably. And based on that, you have a very simple model. And if you have a 5-word history, then this often also disambiguates the specific context. And it's just very hard, unfortunately or fortunately, depending on your perspective. As a system developer, you want to have it simple. But from fundamentally, you would expect that there must be information in that finer grain distinction. Luckily, it works quite well with those very simple models. And that's a general theme, I think, that also you see for a lot of the models that we are doing. If you look at the core of it, it's very simple. but very large amounts of data then help to build very good
Thank you.
models.
Hi, Jeff Coppola, Sandia National Labs. My question concerns machine learning. Probably everybody on the panel is too young to remember, but back in the late 80s, there was a book that came out, Women Who Love Too Much. And then within a few weeks, there was a joke that there was another book coming out, Women Who Love Too Much, and those women's phone numbers fully cross-referenced and indexed. What I worry about in looking at how effective these machines are at learning is that it seems like it'd be a piece of cake to put together an algorithm to find people who are readily exploited. And let's just take a small example. For instance, blackmail. If you were to troll the web and look for terminology and patterns of exchanges that indicated some criteria for being able to blackmail somebody, let's say it's infidelity or, you know, cheating on your taxes or what have you, it just seems like based on the way, the wealth of data that you have, the robustness of the algorithms, and the extent to which we're putting all kinds of information on the internet, it just seems like both inevitable and quite straightforward to be able to develop algorithms that would allow, you know, unethical people to badly exploit and efficiently exploit a lot of people on the internet. I just wanted to get your comment on that.
We're not allowed to discuss features before they're released. So. But no, I didn't mean to short circuit. I think it's a valid question. I shouldn't have made the joke. I'm sure that some other people have something meaningful to say about this before we move on to the next question.
So it is certainly true. If you look at how technology, their advances, and what's possible, and to some extent what we can do here at Google now, which sometimes, right, other people would just a hard time replicating because of the computational resources that just would not be available in other places, then you kind of can look a little bit into the future of what will be possible. Right, Moore's law will most likely in one form or another continue to make it easier for running algorithms which now run on 1,000 machines or 10,000 machines, that in a few years you can just run it on your mega desktop that you'll have then. So this is certainly a challenge which society will have to deal with. A lot more things will be possible, and we run into those things. So for Google Goggles, for example, that recognition, there could be very fancy face recognition in there, but then the question is, right, would that be a good thing or not? So there was a decision made that we wouldn't provide this very fancy face recognition there because it would allow you to do things which probably would allow random people to do things which might be problematic. So this kind of privacy and security aspects will have to evolve over time, and a lot of meaningful discussions are to be had there, and society has to deal with the new possibilities that not only the good people will have, but also the bad people.
So I'm old enough to say that I was entering grad school at the time when people had enough data to look at network traffic and see that it was actually fractal and self-similar as opposed to being Poisson related, which was the early predictions of the internet that the data would be modeled that way. So you guys are analyzing an unprecedented amount of data. So are we about to see some of the normal conventions or theories about what happens in machine learning or information theory or dimension reduction machine learning applications sort of overturned simply because they haven't had enough data to look at?
One of the things that we've discovered along the way is that a lot of the machine learning techniques that have been successfully tried in the past have really been solving the problem of not enough data. And when you start trying to scale those techniques and trying to apply them to a lot more data, then they don't work anymore. They don't really provide any edge, because a lot of the work was really about compensating and making things more robust to lack of information. And over, we see very successful algorithms that were developed in the past really become irrelevant. And much simpler algorithms, if they scale, really take over. So language modeling, we have the old classic n-gram language model. It works extremely well. It scales extremely well. You can throw a lot more data at it, and it works even better every time you add data at it. It's very stupid. People really hate that model because it's too simplistic. But it's very simple, and it scales. And so we see a lot of those patterns emerge over and over where, yes, there is a lot to be learned, and a lot of things that we thought were true before don't really apply anymore.
And a simple generalization of that pattern, which I think both people at Google and in academia are also discovering, is this notion of distribution drift. That, classic machine learning tells us that models with fewer parameters are always better, and models that retain less information are better, right? The VC dimension thing. But then it turns out, the way Vincent described, if you build these models that are essentially smartly memorizing, right? The N-gram models are essentially learning a lot about your world, but in a sort of a smart way. Those models tend to have much better robustness when your world changes, which happens pretty often. That's one common pattern I see across many different areas, where this old lesson is starting to be viewed differently, because this notion of changing world was not commonly analyzed in machine learning before.
You find a list of the things that are not valid. Can you just send that to me?
So my name is Eric Luthart from Washington University. A lot of your models are informed by data that's being explicitly put in by the human users, kind of labels and so forth. Are you at all looking at stuff that's not explicitly put in? For instance, with video conferencing, you have facial expression, or even pupillary diameter, things that could give you physiologic or emotive information about the content that is essentially not entered by that person, or that group of people, or that large corpus of information.
Well, so I guess a lot of the annotation which is learned from is in some sense is given by the person, but not as an explicit label, but by dealing with the system. So spelling corrections, or the example that Alfred yesterday gave, where the system learns from queries and clicks, then it's not that the user annotates, oh, I have here a spelling mistake, but it right. So currently the video, your laptop is not monitored when you type in the search queries. Right.
Yeah, I mean, in the place recognition example I gave, we get a lot of data with GPS tagged images. That's something users don't put in. The camera puts it for them, and we can leverage it once we get it in our pipeline.
And certainly for music, I mean, it certainly would be nice if your phone came with you and decided you're in the car, figured out where you are, like you said, the GPS stuff. And on the other side, on the data analysis, I think it's interesting to look for features that came from the generation of the content as well, like for music expressive timing and dynamics, things that aren't so explicit in the signal, higher level emotive things.
So, okay,
Chris,
last question.
Semper Bio. I was wondering, will some of the OCR techniques be able to improve to the point that they could be used for forensic applications like fraudulent art or handwriting identification or other types of forensic biology?
That's very possible, but that's certainly not our focus right now. It might be hard. I don't know. I haven't really looked into that. I suppose it's possible at some point.
Okay, so we'll have to stop because we're about 10 minutes over time. Thank you all so much for listening. Thanks for the questions. And I hope you have a better idea of now about some of the fascinating problems that we work on at Google. So we'll now be heading to Trader Vic's. All the panel members will be joining us there, so you can also catch up with them one-on-one if you have any questions.
Thank you.